If you know the internal structure of the machine, collect the data where there will be a good solid path to the transducer. We need to use the characteristics of the sensor to maximize our results. Other limitations are built into the transducers that affect our data. One of these limitations is the linear frequency response range. Sensors are designed to function well in certain frequency ranges. This spectrum from a sensor mounted on a shaker table shows its linear or stable frequency range to be from approximately 2 Hz to 10,000 Hz. Frequencies below 2 Hz or above 10,000 Hz would not be accurate in amplitude. Another sensor must be used that is linear in those ranges for amplitude accuracy. Although a sensor is designed to perform well within its stated frequency ranges, there are resonant frequencies unique to the method of mounting the sensor that greatly affects its linear response range. A resonant frequency is a frequency that an object likes to vibrate at. Every object has at least one resonant frequency. When this tuning fork is struck, it will vibrate at a frequency that is dictated by its design. 3 design factors affect the resonant frequency of this tuning fork or any object. These factors are stiffness, mass, and damping. Increasing stiffness raises the resonant frequency. On the other hand, the frequency can be lowered by increasing mass. Finally, adding damping reduces the amplitude with little frequency change. The effect of resonance on your data is vibration frequencies that occur in the resonant frequency range of the transducer will be amplified by as much as 20 times. Therefore, it is important to know the limitations of the selected transducer and the manner in which it is mounted. This long stinger or probe is useful for reaching hard-to-get places and for reaching through a mesh guard to a bearing. However, this probe should not be used for general points because of the amplitude inaccuracies beyond its resonant frequency, which is approximately 300 Hz. Since many problems you want to detect occur outside this frequency range, it is not the ideal tool to be used with a sensor. This 2-inch stinger is also a very handy tool and may be part of the standard accessory kit with your analyzer. It is handy because it allows places to be reached that could not be accessed with a magnet or other mount. The linear range of the sensor with this 2-inch probe is approximately 500 Hz. This would be suitable for many machines that have shaft turning speeds ranging from 1,000 RPM to 1,800 RPM. This magnet has a powerful grip and 2 bevel bars or poles that will fit well on most flat or rounded surfaces. Using this magnet increases the linear frequencies of the same accelerometer to 1,100 Hz. Therefore, it can be used acceptably on shaft speeds to 3,600 or 5,000 RPM and acquire the data you need. This small magnet has a flat surface for mounting. To avoid erroneous data due to unstable mounting, it should be used only on flat surfaces. The linear range of the same sensor with this magnet mount increases to 1,600 Hz and makes it even more desirable if the mounting surfaces are flat. There are instances when even this frequency range is not high enough. When a couplant fluid is used between the sensor and the magnet and machine, the linear response range is increased in this accelerometer to 5,000 Hz with less than a 10% variance. Typical couplant fluids can be a light oil or grease or even petroleum jelly. All of these magnets provide a greater frequency response range than either the 8-inch stinger or the 2-inch stinger. Another benefit of the magnets over the stingers is they hold themselves on with the same force time after time to give you greater repeatability for your data month after month. Studies have shown that data varies substantially depending on the pressure used with a stinger. When data is collected by different personnel, the data varies even more, which makes trending data risky at best. For this reason, it is often difficult to get good repeatable data with handheld mountings. This Quick Connect sensor mounting has the benefit of being placed at exactly the same location from one survey to the next, and it goes in place quickly. The response curve is linear over a longer frequency range and even exceeds the magnet mounts. Another method of mounting sensors is to stud mount the sensor in a pre-drilled, pre-tapped hole. This mounting method provides the greatest linear response range and will give the best, most accurate, repeatable data. Whether your sensor mounting is a stinger, magnet, quick connect, or stud mount, collect your data using the same sensor type, the same sensor mounting, and the same locations time after time. The next consideration is the settling time of a sensor. When a sensor, especially a magnet-mounted one, is placed on a machine, it tends to smack the machine and shock the sensor. Let's look at this as the next point is taken. Many G's are imparted into the sensor as it is placed on the machine. This causes extreme amplitudes and will take 3 to 5 seconds for the levels to settle down. If this energy is included in the spectral averages for the measurement point, the data will be corrupted and of no value to the analyst. The same consideration needs to be made when powering a permanently installed sensor from the panel. Each time a powered cable is connected to the sensor, the voltage shocks the sensor in much the same way and requires the same settling time. Be sure to allow 3 to 5 seconds settling time after placing the sensor on the machine or connecting a powered cable to a permanently installed sensor. Another common data corrupter is the effects of triboelectric noise. All this means is slight movements of the cable during data collection produce changes in the way signals travel through the cable, and these changes are magnified by the signal processing. Let's look at the effect of cable movement during data collection. Notice the sudden rise in energy at the low-frequency end of the spectrum. This is often referred to as a ski slope because of its shape, but is commonly due to triboelectric noise or cable movement. The ski slope is especially common when data is acquired with a stinger because of the slight continual movement of the hand and cable. During data collection, be sure to avoid cable movement, as that may add a ski slope to your data, causing unusually high readings. As we have seen, there is much more to data collection than just placing a sensor on a machine and expecting a complete and comprehensive diagnosis. To acquire the best data for the most complete diagnosis, we need to know the limitations of the sensor, determine the measurement locations that provide the best path of transmission, and mark the machinery to ensure repeatability. During data collection, allow for settling time and avoid cable movement. When an alarm is triggered, collect high-resolution data and take notes of any observances. Never leave in the field what you may need in the office. Thank you for selecting CSI for your technology and product-specific training needs. We look forward to assisting you in your future endeavors.